So, giving this example, chloroform would be better solvent. Both CaCl3 and methanol are polar. So, chloroform would be the better solvent. They both are methanol, HCl are polar and slightly acidic. Although methanol have slightly higher dipole moment, CH3 is likely to solvate the coal tar more easily because methanol tends to form strong hydrogenated bonds with itself. So if you can feel that Cl3 and CH3OH, it will make so if there is a coal tar, it will try to form a hydrogenated structure like a hydrogenated hydrate, and but CHCl3 is likely to solvate it. So there's a solvation happening. This solvation happening. It will solvate the coal tar more easily. Okay. Now another question. So if you have understood, chloroform will be the better solvent. Both CaCl3 and methanol are polar and slightly acidic. Although methanol have slightly higher dipole moment, CaCl3 is likely to solvate the coal tar more easily because methanol tends to form strong hydrogenated bonds with itself. So why it will form with itself. So there will be like OH molecule, and it will itself form because of the OH group which has been present. So it will itself form like this. If you will see, if you know like water, it will itself form bonds with itself. Got it? So, and whereas CaCl3, it's nothing, it's a bit more slightly acidic. Both are polar and slightly acidic, but methanol have slightly higher dipole moment because it won't, and it will likely to solvate it. Okay, so our answer becomes B. So at room temperature, the two solvents are considered. So they wanted to dissolve this coal. So if they had this coal and they put two things, they were asking those questions, and I hope we got the answer. Let's see another question. At 25 degrees Celsius, a binary liquid mixture contains non-polar. So what it contains? Non-polar components 1 and 2. Data for the dilute regions of this mixture indicate that y1 infinity equals to 9.3 and y2 infinity equals to 4.7. At 25 degrees Celsius, it is asking the correct range for the instability would be. At 25 degrees Celsius, a binary liquid mixture contains non-polar components 1 and 2. Data for the dilute region of this mixture indicate y1 and y2 infinity. At 25 degrees Celsius, the correct range for the instability would be. So we're using 3 suffix to constant Margulis equation. So this is the Margulis equation. G by RT equals to x1 x2 a plus b x1 plus x1 minus x2. We obtain ln gamma 1 equals to the same way as a plus 3b x2 square. So by this Margulis equation, we obtain ln gamma 1 and ln gamma 2 as a minus 3b x1 square, and this is 4 beta x1 cube. So a plus 3b a minus a, and this is the beta which we have. Okay, at infinite dilution this will become a minus b. So at infinite dilution x1 tends to 0, next 2 will become 1. So solving both equation, we got gamma 1 infinity. We already know gamma 1 infinity and gamma 2 infinity. We get a and b value. So it has already been given. For instability to occur, so basically we have already been given these gamma 2 and gamma 1 value. So gamma 1 infinity, putting the gamma 1, first of all we just did at infinite dilution how much it will be the value. So it will be approximately a plus b and a minus b. Did you get how much you get? So this is b. Okay, so if I'll put infinite dilution, x2 tends to 1, so putting a plus 3b minus 4b, so this will give approximately a minus b as value. Gamma 1 will be infinity since we have been given that value. Gamma 2 in its same way, x2 tends to 1 because infinite dilution is there. So similarly x2 tends to 1, a minus 3b plus 4b, which will be equals to a plus 4b. Solving both, because we already have this value 9.3 and 4.7, taking that we get, if you will solve this question for a minute, we'll get a equals to 1.89 and b equals to 0.34. For instability to occur, this is the formula, that del square g square del x1 square pt and rt equals to 1 by x1. So this an information, or we already know that this is what you say condition. This is the condition for the instability to happen. Rewriting GE, so we already had GE as x1 x2 a plus b x1 minus x2. So doing this, G equals to minus b 3 x cube, and then we'll be doing G equals to RT a minus b x1 a minus c x1 and 2b x1 cube, and then we'll solve it del square by x1, the basic differentiation which we have to do twice. So a minus 1 x1 and so x1, and then it will do 2 minus 3b minus. Thus the condition for a constant becomes, so you have to just put less than 0, finding the 0. So you just have to find this value For this value, you went ahead with differentiating the value, and we got x1, finding the 0. So you find the x1 and putting 1 minus x1, and you know these values already. 12p values, you have already the values of a and b. Put those, putting the value of finding the zeros of the function in brackets. So basically whatever the function we got, if you just want to take it, take the denominator as x into 1 minus x1 and try to find these values as x1 square, some value plus constant you will get, in 1x1 you will also get. So when you solve it, it's a quadratic equation, so it will become 0.421 and 0.352. You can try solving this for a minute and see that it will be in the range of x1 is in the range of 0 to 1, thus instability will be in this region. It's a good question. Let's check. For an extraction separation for n hexane, which of the following should be the characteristic? Strongly hydrogen-brittle liquid. Example, water and most alcohols would be poor solvent. So for an extraction separation of hexane and hexene, which of the following should be the characteristic of this term? Strongly hydrogen liquid would be poor solvent, strongly hydrogen would be good solvent, a Lewis acid would be a good solvent, none of these are. So you can try solving this. So this is which of the following should be. So the solution is strongly hydrogenated bonded liquids would be poor solvents. The reason is it is important that the solvent should be something that prefers self-interaction than that with hexene molecules. Strongly hydrogen molecules, example what, would therefore be poor solvent. A weak Lewis acid will not be. So this says it is important to note that the solvent should be something that prefers self-interaction that with hexene molecules. Strongly hydrogenated bonding would therefore be a poor solvent, because if H2O or H2 is there, they will themselves make an hydrates, right? So they will be a poor solvents. A weak Lewis would not be a good solvent. So a weak Lewis acid will not be a good solvent. We want a Lewis acid that can look for a double bonds in hexene. A strong Lewis acid will be a Lewis acid, a strong Lewis acid, because this is a weak Lewis acid. because it will make their own hydrates, because you see that they want a self-interaction. I prefer self-interaction than with the solvent should not be something that prefers simple interaction. So water or OH alcohol like methanol, ethanol, they will have their own self-interaction. Whereas they don't want to be poor because they want hexene to be. So what is it? It's like hexene to be mixed with. So extraction, separation of hexane and hexene. So something which gets mixed with the hexene. So if we know that a hexene, if someone there, so it should get mixed by this. It should not prefer self-interaction by themselves. So it should not have, like, this is a good point. They should not have a self-interaction with themselves. A weak Lewis acid, so a weak Lewis acid would never be a good solvent. We want a Lewis acid that can look onto the double bond. And so let's do another question. At 380 Kelvin, an equimolar liquid mixture A and B has a total pressure of 0.667 bar. Fluid A and B are simple non-polar liquids having molar volumes. Pure component vapor pressure are this and this. If the equimolar is cooled, partial miscibility, give an estimate of the critical temperature where partial miscibility begins. So at 380 Kelvin, an equimolar liquid mixture of A and B has a total pressure of 0.667 bar. Fluid A and B are simple non-polar liquids having these volumes, and if the equimolar mixture is cooled, partial miscibility, so you need to give a critical solution temperature where actually partial miscibility begins. So you need a critical to find this as a critical temperature for this, and it gives a hint. Since the two fluids are similar in size, simple and non-polar, assume that gamma S are given by 2 suffix Margulis equation. So neglecting vapor pressure, non-idealities, and pointing correction, the total pressure, as we know, now we have used this equation a lot. We already have ln gamma 1 in some form of an equation as xa plus xb equals to 0.5. We just put these values and we got A and Tc equals to 282 Kelvin. If you'll see, neglecting vapor pressure and non-idealities, we just directly wrote it xa and xb equals to 0.5 because equal. So P equals to 0.667. So this was already given to us and we just added both the equation. And got the uppermost limit as 282 Kelvin, because then the idealities will start. So this whole lecture we did some of the distillation column questions. So I will be uploading this lecture, this as part 1 and part 2. So I hope you like the lecture and I'll be uploading this with